Oh, hello, and welcome to another nice video from college algebra. This time it's about linear programming, a type of linear inequalities that does exactly this. Takes a word problem with lots of information that you need to organize and make some equations out of, and then see where all of those things cross. And where they cross is going to be some points that you're going to have to want to maximize or minimize with a cost function or a profit function. Okay, so there's lots of things to do here. It's very important to keep all of your P's and Q's and all of your ducks in a row. Okay, but organizing your information so that it makes sense is the most important part of any of these linear programming problems. So I have 3 examples for you today. Feel free to skip one to the next one if you don't need to do one of these types. But there's 3 different ones here just for you. Okay, I gotta move this out of the way. Okay, Sally and George. Here we have a pretty basic problem. Okay, Sally and George, 2 people have a car and a truck. Okay, the car gets 34 miles per gallon and has a 16-gallon gas tank. The truck gets 18 miles per gallon and has a 24-gallon gas tank. And they can afford to split 30 gallons of gas per week between the 2 vehicles. Okay, that's all the information that we're given. That's your setup. Now here are your questions. How many gallons should be put in each vehicle to maximize the miles driven? And then what is the maximum number of miles, or what are the maximum number of miles? So there's basically 2 questions that we're trying to find here. Okay, how many gallons of gas should be put into each vehicle? Okay, we only have a limited supply, so we can't just fill them both up. Okay, that would be too many gallons right here. 40 gallons if you're going to fill them both up all the way, but we can only afford to do 30 gallons of gas. Okay, they're on a budget, they are living within their budget, so they've budgeted 30 gallons of gas and do not want to exceed that. Okay, so here's how we're going to organize our information. We have a certain number of things, your items I'll call them. Okay, so in this case, Sally and George own a car and they own a truck. Okay, car and a truck, those are the items. So up here we're going to have some attributes of these 2 items. Okay, so we have miles per gallon. That's an attribute of the car. Okay, the car gets 34 miles per gallon and the truck gets 18 miles per gallon. Okay, this is what we were trying to maximize, how many miles we can drive on a certain number of gallons. So this will be important later, but not for just right now. Okay, the next constraint that we have is the tank size. The tank size. So the car only has a 16-gallon tank, and the truck has a 24-gallon tank. Okay, and together they can split 30 gallons of gas. So that's kind of an aside down here, another piece of information that they have to split 30 gallons of gas. So the total number of gallons of gas they have is 30 gallons. Okay, that doesn't go with the car or the truck. It goes with both of them. Okay, it goes with the car and the truck. Together they have 30 gallons of gas. Okay, so now that we have our information organized, let's write down some equations. Okay, so this is what we want to maximize. You want to maximize your miles per gallon. So the number of miles that you're able to drive is given to you by 34 miles per gallon in the car. So 34 miles times however many gallons you put in the car, plus 18 miles times however many gallons you put into your truck. Okay, so this is the maximizing function. We want to see as many gallons as we can here and as many gallons as we can there in order for us to be able to do everything that we need to do. Okay, so we want to maximize the number of gallons here and the number of gallons there. Okay, so 34 gallons and 18 gallons. So we know together that the car plus the truck, the number of gallons you put in the car plus the number of gallons you get in the truck cannot exceed 30 gallons. So there's one of your inequalities here. Okay, inequality. Car plus a truck has to be less than or equal to 34. And then the other 2 are your constraints, your car constraint. Your car cannot hold more than 16 gallons of gas. okay, all by itself. And your truck cannot hold more than 24 gallons of gas, all by itself. So your three inequality equations that you're going to graph are these three. Okay, all by themselves, the car and the truck have their own constraints. They can't have more than 16, can't have more than 24 out of the 30 gallons. So you put them all together. So let's go ahead and graph these three equations. So on the next slide, I have some graphs here. Remember, we had the car was less than or equal to 16 gallons. The truck was less than or equal to 24 gallons. And together, they could not exceed 30 gallons. So here I have some axes. I have a dependent and an independent. So it really doesn't matter which one you call which, but let's just for fun say that this is your car axis and this is your truck axis. Okay, so your car represents the x variable, the truck represents the y variable. Okay, so if the car is less than or equal to 16, I'm going to graph that onto here. Let's call our units, I don't have 30 ticks, so 2, 4, 6, 8, 10, 2, 4, 6, 8, 20, 2, 4, 6, 8, 30, and so on and so forth. 2, 4, 6, 8, 10. Let's stay consistent. 2, 4, 6, 8, 20, 2, 4, 6, 8, 30. So if the car has to be less than 16, 10, 12, 14, 16. Okay, I have a vertical line because it's the x-axis, so represented by the x-axis of the vertical line. So I can put in as much as 16 gallons of gas. So any one of these would be an acceptable answer. Everything less than 16. Shade it all the way up like we shade inequalities. Okay, your truck is less than or equal to 24. So here's your truck's axis right here. So the truck cannot exceed 24. So now we have reduced our potential answers. So all of these are potentials. I could put 2 gallons of gas into my car and 4 gallons of gas into your truck. Okay, that's an answer. I could put 6 gallons of gas and 8 gallons of gas. I could put 10 gallons here and 0 there. All of these are potential answers. But it's not going to be the one that maximizes my equation. Okay, remember, I want to get the maximum number of miles I can. So now I have to graph this equation. So c plus t, remember t is your y variable, so if you solve this equation for t, 30 minus c, that has a y-intercept of 30, and it has a -1 slope. So this is the graph of my equation, t equals 30 minus c. So the number of gallons of gas I can put in my truck is 30 gallons minus the number I put into my car. So I get this nice linear equation here. So now that we have this equation, we further minimize our options. Okay, some of these are not even optional anymore. Okay, but what we're trying to do here, now we have some nice points. Okay, let's do this in green. So I have this point here is an intersection of two lines. This point here is an intersection of two lines. So where all of these things intersect, it turns out that your vertices are going to be where you can have the maximum or minimum amounts. Okay, so this point here, this point is 6 gallons of gas in your car and 24 gallons of gas in your truck. That is a possible way to split the 30 gallons of gas. 6 gallons in your car, 24 gallons in your truck. Okay, here's another option. 16 gallons in your car and only 14 gallons in your truck. Okay, this is another way that you can split your 30 gallons of gas. 16 and 14 is 30, 6 and 24 is 30. And all the other stuff. So now we need to figure out, remember we had this maximizing equation. We know the number of miles is the miles per gallon of your car plus the miles per gallon of your truck. So now I have two options that I need to test to see which one is best. Okay, there's your 624 option. 6 gallons in your car, 24 in your truck. Or there is the 1614 option. 16 in your car and 14 in your truck. So let's see. Remember, the profit function was 34 miles per gallon, so 34 miles times 6 gallons plus 18 miles for every 24 gallons. Okay, or down here, we can drive on a P, let's just call it M. M for miles, sorry, P is profit. M for miles. The miles is 34 times 16 plus 18 times 14. So let's get my handy dandy calculator out here. Let's see, 36 times, sorry, 34, clear that. 34 times 6. Okay, that's 204. 18 times 24 is 432. So if I add these both together, I get a grand total of 636 miles that I could drive, 6 gallons in my car and 24 gallons in my truck. Okay, let's see if I can do better down here with this other equation. So 34 times 16, that's 544. 18 times 14, that's 252. So if I add these two things together, I get a total of 796 miles. Okay. So it would behoove me, very much so, to put 16 gallons of gas in the car and to put 14 gallons of gas in the truck. Okay, that way, if I split up my gas that way, I can drive 796 miles. Okay, that's the maximum number of miles I can drive when I do this option. Fill up my car completely and put only 14 gallons in my truck. Because remember what my questions were. My questions were how many gallons should be put in each vehicle and what is the maximum number of miles. So you should put 16 gallons in your car and 14 gallons in your truck to be able to drive 796 miles. Okay, like I said, these probably take a while and they have lots of thoughts. You really have to organize your information. You have to be able to graph that information, and then you have to interpret your graph and see which is your best option. Okay, linear programming, tons of fun. Okay, let's take another of, another example here. Manufacture 2 sides of gears. So our things that we're doing, our items, let's organize this as we go. 2 sizes of gear, smaller gear and a larger gear. So these are the 2 things that we're making. We're making small gears and large gears. Okay, so let's identify that first. Small gears and large gears. Now, what about the small gears? The small gear requires 4 hours of machining, so we got to actually make the gear itself. It takes 4 hours to machine a small gear and 1 hour of polishing. So we have another attribute that is polishing. To make it nice and shiny, it takes 1 hour to do that. Okay, 1 hour, not natural log, 1 hour. And yields a profit of $25. So here's another thing, the profit. Remember, this is how much money we want to make. We want to make this maximum. $25 for every small gear that we sell. Okay, 3 pieces of information about your small gear. The second one, the large gear requires 1 hour of manufacturing or machining. So it takes 1 hour here. And requires 1 hour of polishing. So let's see, purple is polishing, so 1 hour of polishing. And yields a profit of $10. Sorry, that should be in blue. Profit of $10. Okay, now let's see what else. The firm has available at most 24 hours per day. So here are your limitations. We cannot exceed these things. Okay, 24 hours a day for machining and 9 hours each day for polishing. And our questions: how many of each gear should be made, and what is the maximum profit? Okay. If you organize your information in this way, notice my color coding, I get one equation that's all about machining times. 4 hours for small gears, 1 hour for large gears, 24 hours total. So the small gear has machining time, large does, and then I have a total number of hours that's not to exceed. So I organize my information so that this becomes one linear equation. Okay, likewise, I have another one. All of these things have polishing. Okay, I have 3 different things that need polishing. I have a small gear, a large gear, and a total time to polish. So these are going to be your 2 equations, and then this is going to be what we're trying to maximize. Okay, make it the biggest possible. So let's go ahead and write our equations on this next page here. Okay, you can pause it and come back if you like, but I'm going to go ahead and do this. So we have our machining time. Okay, so let's make the small gears your x variable and the large gears your y variable. Small is x, large is y. So I have 4 hours to make small gears, and I have 1 hour to make large gears, and that cannot exceed 24 hours for machining. And then I had the polish. That was 1 hour for small gears plus the 1 hour for large gears, and that was only 9 hours. Okay, so here are your linear equations. We have an x variable, a y variable, and a total. Okay, so this is not an equation we're going to graph because it doesn't have a third variable, a third thing that is related to it. So this is our profit function. Okay, so now that I have this, okay, x is here, small gears. Small gears are your x value. Large gears over here, large gears are your y value. We need to solve both of these equations for y so that we can graph them. Or if you want to use the intercept method, that's fine as well. So y is less than or equal to negative 4x plus 24. Okay, you bring the 4 over, it's a subtraction problem. Down here, simply y is less than the negative of x plus 9. So now we have to graph both of our equations so we can see where they intersect. Okay, 24 on the y-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like it's going to be off of here. So I'll make 24 way up here. 1, 2, 3, 4 over 1. Okay, this is 20 by the way. Down 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. And we keep graphing this using the slope. So it crosses here at 6. Okay, so this is the line that represents the amount of time that it takes to machine or to create, to manufacture small gears and large gears. So all of these down here, this is our potential hours that we can devote to small gears and large gear creation. Okay, we could do 1 hour to small gears and 1 hour to large gears. We wouldn't make very many of anything, but that's a possibility. So now we want to see when this one, negative x plus 9, so it crosses at 9, 3, 4, 5, 6, 7, 8, 9. And it has a negative 1 slope. So down 1, right 1, down 1, right 1, down 1, right 1. Okay, and of course we could stop already because we see where it intersects, and that's the important thing, is where do these graphs intersect. Okay, so this limits our stuff even more. So here we have our nice quadrilateral. The intersection of these two areas is going to be your solution. Okay, so we need to try each of these vertices, but it's going to turn out that this one where they cross will be where it's going to be maximized. So it looks like that is 5 small gears. Okay, 5 in the small gear and 4 in the large gear. So from your graph, you can see where they cross, and that crossing point is what we're going to use to tell our boss how many things we should make. So let's go on and calculate some things. So for 5 small gears and 4 large gears, the profit is going to be, let's go back here and see our profit function. You make $25 for every small gear and $10 for every large gear. So $25 for every X plus 10 for every Y. So 25 times 5 plus 10 times 4. 125 plus 40. Looks like we would make a profit of $165 on those 5 small gears and 4 large gears that you would make. Okay, so once again, walk through the steps. Organize your information. Okay, get equations. Anytime you have 3 things, you have a variable for the first one, a variable for the second one, and then a third constraint placed upon those 2 variables. And then you have your profit or your cost function at the very, very last. Okay, you take those, you graph them, so you solve them both for y. You graph them, you see where they cross. That is your answer. Okay, if you happen to have 2 crosses like the last one did, then you have to try them both into your profit function to see which one would make more money. Okay, because that's what you want to maximize, meaning you want the most possible. Alright, so there's another example. And here is still a third example. Let's see, an animal feed to be mixed from soybean meal and oats must contain at least 120 pounds, 56 pounds, 26 pounds of ash. So protein, fat, and ash. Each sack of soybeans, so we got some information about soybeans, we got some information about oats, and then how many of each should we buy, and what would be that smallest cost. So let's organize our information. What things are we talking about? Okay, we're talking about sack of soybean, and we're talking about sacks of oats. So soybeans and oats. Okay, so let's see, what about soybeans and oats? Well, they each have some protein. Well, they each have a cost, first of all. Let's do the cost. Soybeans cost $15. Oats cost $5. Okay, what else do we have? Each sack of meal contains 48 pounds of protein. So protein. Um, 48 pounds of protein. And down here, oats have 12 pounds of protein. What else do we have? We have some fat, so 8 pounds of fat. And down here, another 8 pounds of fat in our oats. And then our last variable is going to be the ash. So we have 2 pounds of ash in the soybeans, and we have 6 pounds of mineral ash in the oats. Okay, and now the stuff up here at the top. This is what we want. We want to have at least, so this is going to be a minimizing equation. At least means this is the smallest amount that we could possibly accept. 120, oh, that's not cost. 120 in protein. So at least 120 in protein, at least 56 in fat, and at least 26 in ash. Okay, so here's your cost function. That's what we want to minimize. Notice there's not a third variable down here, so this is your cost function. Here's one equation, here's 2 equations, there's 3 equations. Okay, so we have 3 different things to contend with, so we have 3 different equations. So let's go over here and let's make our equations. Okay, protein. Protein. Okay, so we had 48 soybeans, which we'll call X, and oats we'll call Y. So 48 proteins plus 12 oats has got to be bigger than 120. 48 plus 12 has to be bigger than or equal to 120. Okay, at least means this stuff has to be at least 120. Larger, preferably, but smallest it could possibly be is 120. Okay, and then fats, we have 8 soybeans, 8 oats, and we want 56. So fats, 8x plus 8y has to be bigger than or equal to 56. And our last one was ash. We have 2x plus 6y needs to be bigger than 26. 2x plus 6y is bigger than or equal to 26. Okay, so remember this is your soybeans down here, your x-axis, and this is your oats on your y-axis. So we need to take each of these equations and solve them for y. Okay, so you take your 48, you subtract it over to that side. 12y is bigger than, let me get this really small. Negative 48 plus 120. Divide everything by 12. So you get y is bigger than or equal to negative 4x plus 10. Okay, that's one equation that we'll graph. Okay, solving this one should be pretty quick. Y is bigger than or equal to negative x plus 7. When we subtract the 8x, which is why it's negative, and then divide everything by 8, you get this equation. And then lastly, you subtract the 2, you get y is bigger than or equal to negative 1/3. 2 divided by 6 is 1/3 x plus 26 divided by 6 is 4 and change, 4 and 2/6, 4 and 1/3 or so. So here are your 3 equations that we need to graph. And let's see where they cross. So 4x, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Down 4 over 1, down 4 over 1, down 4 over 1. Negative 4x plus 10. Well, how about I do this? I'm going to make each one of these things 1/2. We'll do that. Let's erase this. I have enough room. 10 is my biggest value. So this is going to be 1, and this is going to be 2, and this is going to be 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. That's better. It gives us a little bit more room to operate since it's very small numbers, or relatively small, not 20s and 30s, but. Okay, there's that one. Now our blue one, 7, so crosses here, and here's a -1 slope. So it goes along this -1 slope. So that's nice, it crossed right there. Now remember, these are minimums. So we're trying to graph anything out in the larger section. So it's all of this over here. This is what we're trying to achieve. These are minimum values. What's the smallest number we want to buy? And then the red one, 4 1/3. Somewhere in here maybe. Down 1 over 3. 1, 2, 1, 2, 3. 3 1/3. Down 1 over 3. Down 1 over 3. Here we go. Okay, so here we have, looks like 2 points of intersection for your potential answers. So we have 1 point right here, which would be 1 thing of soybeans and 6 things of oats. 1 comma 6, or over here 1 2 3 4 5 soybeans and 2 oats. Okay, so those are your 2 points of intersection on your graph. Remember, it's everything out here, so this is a minimum requirements. So now let's go back to our cost function. It costs $15 for every soybeans and only $5 for every oats. So here we have our cost function, 15 for every soybean plus 5 for every oat. That's your cost. So let's try the points. Let's see, what were those points? 1 comma 6, 1 soybean, 6 oats. Let's try 5 comma 2. Sorry, wrong way. 5 soybeans and 2 oats. Okay, so let's see, 15 times 1 plus 5 times 6, 15 plus 30, so it would cost us $45 if we got 1 bag of soybeans and 6 bags of oats, or 15 times 5 plus 5 times 2, 75 plus 10 would cost $85. Okay, so because we want to minimize this, we want the smallest possible, it looks like we should buy 1 bag of soybeans, or 1 sack, whatever, 1 bag of soybeans and 6 bags of oats. Okay, that would give us our minimum requirements of subsistence, but it would cost the least amount of money to buy 1 bag of soybeans and 6 bags of oats, rather than 5 bags of soybeans and 2 bags of oats. Okay, so there are some options. When you have multiple points, you got to try them both into that function, into your equation. When you only have one option, like over here on the second one, then it's pretty nice and simple. This is the only right answer. There's only one option. Okay, so remember, the hardest part is keeping all of your facts straight. Okay, so if you try to organize it like this, hopefully after a couple trials you'll be able to get it. They're not easy, they are kind of long and arduous sometimes, but it's great algebra, and the answers are really show your knowledge of what's going on with inequalities. Okay, so good luck, have fun, try to do your best, and we'll see you on the next video.